welcome to this problem walkthrough. Today, we'll explore problem number 1972, last day where you can still cross. This problem challenges us to determine the last day when it's still possible to navigate across a grid as cells incrementally flood over time. Get ready to dive into an interesting algorithmic solution. In this problem, we are dealing with a 2D grid that has rows and columns. Initially, all cells in this grid are unblocked, meaning you can move freely through them. We are given an array cells where each element cells I equals R C tells us that the cell at position R C becomes blocked on the ith day. The goal is to determine the last day when it is still possible to cross the grid from the top row to the bottom row. You can only move through unblocked cells, and the movement is restricted to the cardinal directions up, down, left, or right. The function needs to return the last day on which crossing the grid from top to bottom is feasible. The problem specifies that the output should be an integer representing the last day where crossing is possible. Let's look at an example to understand this better. For row equals 2, col equals 2, and cells equals 1, 1, 2, 1, 1, 2, 2, 2, the goal is to determine the last day when a path exists from the top row to the bottom row. On day 1, all cells are unblocked, so the grid looks like a 2 by 2 grid of zeros, indicating that every cell is traversable. At this point, it is possible to cross from the top row to the bottom row by moving straight down through any column. On day 2, the cell at 1, 1 becomes blocked, represented by a 1 in the grid. The grid now has one blocked cell, but it is still possible to cross by moving straight down the second column, which remains unblocked. On day 3, the top row is fully blocked because both 1, 1 and 1, 2 are now inaccessible. This means there is no longer any path from the top row to the bottom row, and crossing becomes impossible. Therefore, the last day where crossing was possible is day 2. This solution illustrates the importance of tracking which cells become blocked and how that affects connectivity across the grid. In another example, let's consider row equals 2, col equals 2, and cells equals 1, 1, 1, 2, 2, 1, 2, 2. On day 1, the grid shows that all cells except 2, 2 are unblocked, so there is still a path from the top row to the bottom row. You can cross by moving through the first column. However, on day 2, both 1, 1 and 2, 2 are blocked, leaving no viable path from the top to the bottom. This means the last day where crossing was possible is day 1. This example highlights another way in which the grid can become disconnected as cells are sequentially blocked. Now, let's analyze a larger grid with row equals 3, col equals 3, and cells equals 1, 2, 2, 1, 3, 3, 2, 2, 1, 3, 3, 1, 1, 1, 3, 2, 2, 3. On day 1, only the cell 1, 2 is blocked. The grid still has multiple paths available, such as moving down the first column or navigating through the middle of the grid. It's clear that crossing is possible at this stage. On day 2, additional cells are blocked, but there is still a path through the grid if you navigate carefully. This demonstrates that even as cells are progressively blocked, crossing may still be possible depending on the arrangement of unblocked cells. By day 3, the grid has several blocked cells, but there remains a viable path through the second column. However, as more cells continue to be blocked in subsequent days, the connectivity between the top and bottom rows is eventually severed. On day 4, for example, all paths are completely obstructed, making it impossible to cross the grid. The last day where crossing was possible is therefore day 3. This example illustrates how the problem scales with larger grids and highlights the need for an efficient algorithm to determine the last day of connectivity. Finally, let's consider some constraints and edge cases. For a 1 by 1 grid, the only cell becomes blocked on day 1, so there is no day where crossing is possible, and the output is 0. In larger grids where cells are blocked sequentially, the output depends on when the top to bottom path becomes fully obstructed, which varies based on how the cells are blocked. For the maximum grid size of 2000 by 2000, the solution must be efficient to handle up to 4 million cells. This requires careful implementation to ensure that the algorithm performs well within the constraints. To solve this problem, one approach we might consider is the brute force technique. The idea here is to simulate the process of blocking cells on the grid day by day. On each day, we update the grid to reflect the blocked cells and then check whether a path still exists between the top row and the bottom row. This can be done using depth-first search or breadth-first search. The process stops when no such path is found. However, there are important observations to note about this approach. First, the grid changes incrementally each day as cells are blocked, which means we need to repeatedly check the connectivity between the top and bottom rows. This connectivity check becomes the bottleneck in terms of performance. As a result, this approach is computationally expensive, especially for larger grids where the number of rows and columns can go up to 1,000. The repeated simulation and connectivity checks make it infeasible for such large inputs, as the time complexity grows quadratically with the size of the grid. Thus, while this approach is intuitive, it is not practical for larger grids due to its inefficiency. A more optimized approach involves combining binary search with pathfinding techniques such as BFS or DFS. Instead of simulating the process day by day, we use binary search to narrow down the last day where a path exists between the top and bottom rows. The key to this approach is that binary search allows us to significantly reduce the number of days we need to simulate. For each midpoint in the binary search, we simulate the grid state up to that day and check for connectivity using BFS or DFS. The process involves adjusting the bounds of the binary search based on whether a path exists or not. The result is the last day where connectivity is maintained. This method is far more efficient than the brute force approach because binary search reduces the number of days to logarithmic scale, and BFS or DFS is effective for checking connectivity on the grid. The time complexity for this approach is proportional to the product of the logarithm of the number of days and the size of the grid. This makes it scalable for larger inputs, striking a balance between simulation cost and the reduced number of iterations. By leveraging binary search, we avoid the inefficiencies of checking each day individually. The most efficient approach we considered is the union find, or disjoint set union, method. This strategy works backwards, starting from the last day and unblocking cells instead of blocking them. As we unblock cells, we dynamically merge them with their neighboring cells to maintain connected components. The process stops as soon as we establish connectivity between the top and bottom rows. This approach has several advantages. First, working backwards eliminates redundant simulations because the grid state is incrementally built as cells are unblocked. Second, the union find data structure is highly efficient for managing connectivity checks and merges, as its operations are nearly constant time. Importantly, we only process relevant cells, those that are unblocked, which reduces computational overhead. The steps involve initializing a union find structure for all cells, including virtual nodes representing the top and bottom rows. Then, as we iterate backwards through the list of cells to be blocked, we merge each unblocked cell with its neighbors and check if the top and bottom rows are connected. The earliest day where this happens is our result. The time complexity of this approach is nearly linear, factoring in the inverse Ackermann function, which grows extremely slowly. This makes the union find method the most efficient choice for large grids. Ultimately, the strategy we chose to implement is the union find approach because of its superior efficiency and scalability. By working backwards, we minimize redundant computations, focusing only on relevant updates to the grid. The union find data structure allows us to perform connectivity checks and merges with near constant time complexity, making it well suited for large inputs. Compared to the binary search method, this strategy avoids repeated simulations of the grid state, instead leveraging incremental updates as cells are unblocked. While union find introduces some additional complexity in terms of implementation, the trade-off is worthwhile given the significant performance gains. For large grids, this approach ensures that we can solve the problem efficiently, even for the upper limits of the input size. To solve this problem, we need to figure out the latest possible day when there is still a valid path from the top row to the bottom row of a grid, despite cells being blocked day by day. The path must consist of cells connected in the four cardinal directions up, down, left, and right. The process begins by taking the grid dimensions, m and n, along with a list that specifies which cells are blocked for every day. With this information, we employ binary search to narrow down the day when the last valid path exists. Initially, we set our search range from day 1 to the total number of days. For each midpoint during the binary search, we simulate the grid, blocking cells up to that day, and check if a valid path can still be found. This avoids the inefficiency of simulating every single day, making the process much faster. The simulation involves constructing a grid and marking cells as blocked day by day, while tracking blocked cells in a set for quick updates and lookups. Once we simulate the grid for a given day, the next step is to determine whether a valid path exists from the top row to the bottom row. We can achieve this using either breadth-first search, BFS, or depth-first search, DFS. Starting with all unblocked cells in the top row, we explore adjacent unblocked cells in the 4 cardinal directions. If any cell in the bottom row is reached during this exploration, we know a valid path exists. Depending on whether a path is found, we adjust our binary search bounds. If a path exists for the current day, it means paths are still possible, so we move the lower bound up to search later days. If no path exists, we move the upper bound down to search earlier days. Once the binary search completes, the highest day for which a valid path was found will be stored in the variable representing the result. This approach combines the efficiency of binary search with the localized exploration capabilities of BFS or DFS. By doing so, we optimize the process to find the result quickly, even for large grids and long time spans. In edge cases, if no valid path exists even on the first day, the result should simply be 0 because the grid is already impassable. Conversely, if the grid starts completely open with no blocked cells, the latest day will be the total number of days, since the path will remain clear until the very end. For grid representation, we use a 2D list where -1 marks blocked cells, and 0 marks unblocked cells. To efficiently manage blocked cells, a set is maintained for quick updates during simulations. When implementing BFS, we use a queue to explore the grid level by level, ensuring efficient traversal. Looking at the complexity, the binary search operates in logarithmic time relative to the total days, while each BFS or DFS simulation takes O(m*n) time for the grid traversal. This results in an overall time complexity of O log total_days *m*n. The space complexity is also O(m*n), considering the grid representation and the queue used for BFS or DFS. These optimizations make the algorithm scalable for larger problem instances. The core of the algorithm lies in the function that checks whether a valid path exists for a given day. To start, we create a grid initialized with all cells unblocked. Then, for the specified day, we mark the corresponding cells as blocked using the input list of blocked cells. With the grid prepared, we initiate BFS to determine path existence. We enqueue all unblocked cells in the top row as starting points, marking them as visited. As we dequeue cells one by one, we check if any of their neighbors in the 4 cardinal directions are unblocked and within bounds. If a neighbor is valid, we enqueue it and mark it as visited. If we reach any cell in the bottom row during this process, we can immediately return true, indicating a valid path. This ensures that we are systematically exploring all potential routes through the grid, stopping as soon as the bottom row is reached. If no cell in the bottom row is reached after fully exploring the grid, we return false, indicating that no valid path exists for the given day. With this helper function in place, we implement binary search to find the latest day with a valid path. We initialize the search bounds as 1 and the total number of days, and we maintain a variable to store the result. For each midpoint in the binary search, we call the path-checking function. If a valid path exists, we update the result to the current day and shift the lower bound upward to test later days. Otherwise, we move the upper bound downward to investigate earlier days. Once the binary search completes, the result contains the latest day on which a valid path exists, and this value is returned. This combination of efficient pathfinding and binary search ensures that the algorithm is both accurate and performant, even for large grids and complex scenarios. Here, we start by importing the DEEC class from the collections module, which we'll use to implement a queue for our breadth-first search. Then, we define a method called latestDataCross within the solution class. This method takes 3 parameters, the number of rows, the number of columns, and a list of cells representing the order in which the grid becomes flooded. Within this method, we define a helper function called canCross that will determine if it's possible to cross from the top row to the bottom row of the grid on a given day. The canCross function starts by initializing a grid of zeros with the given dimensions, representing dry land. It then floods the cells based on the first day entries from the cells list. Each flooded cell is marked with a 1. After setting up the grid, we initialize a queue to perform a breadth-first search. We unqueue all the dry cells in the first row, marking them as visited by setting their value to -1. We also define a list of directions, representing the possible movements, right, left, down, and up. Using this, we process each cell in the queue. If we reach the last row during the search, it means crossing is possible, and we return true. Otherwise, for each neighboring cell, if it's within bounds and unvisited, we mark it as visited and add it to the queue. If the queue is exhausted without reaching the last row, we return false, indicating that crossing is not possible on that day. Now, we move on to the binary search implementation. We initialize three variables: left as 1, representing the earliest possible day, right as the total number of cells, representing the latest day, and answer, starting at 0, to store the last day when crossing is possible. While left is less than or equal to right, we calculate the midpoint, mid, and check if crossing is possible on that day by calling the canCross function. If it returns true, it means crossing is possible, so we update answer to mid and adjust left to mid +1 to search for a later viable day. Otherwise, we adjust right to mid 1 to search for an earlier viable day. Finally, once the loop completes, answer holds the last day when crossing is still possible, and we return this value. This approach efficiently narrows down the solution using binary search, combined with the breadth-first search logic in canCross to verify the feasibility of crossing on any given day. Here, we start by defining the method latestDataCross, which takes in the number of rows and columns, as well as the cells matrix representing the sequence of cells that get flooded. We use binary search to determine the latest day we can still cross from the top to the bottom of the grid. The left and right variables define the range of days for our search, and answer keeps track of the most recent day where crossing was possible. Inside the binary search loop, we calculate the midpoint mid, representing the day we are currently testing. If the helper method canCross returns true for this day, it means crossing is possible, so we update answer to mid and shift the search range to later days by setting left equals mid +1. Otherwise, we adjust the range to earlier days by setting right equals mid 1. Finally, once the loop ends, we return answer, which holds the latest day we could cross. Next, the helper method canCross is defined, which determines whether crossing is possible on a given day. We first initialize a grid to represent the flooded state by marking all flooded cells up to the given day in the grid array, where a value of 1 indicates a flooded cell. This prepares the grid for the next part of the algorithm. Now, to determine if crossing is possible, we perform a breadth-first search, BFS, starting from the top row of the grid. We use a queue to simulate the BFS process, and we begin by adding all non-flooded cells in the top row to the queue. These cells are also marked as visited by setting their value in the grid to -1. To explore neighboring cells, we define an array of directions representing the 4 possible movements: right, left, down, and up. While the queue is not empty, we process each cell by dequeuing it and checking its neighbors. If we reach the bottom row, it means we successfully found a path, so we return true. Otherwise, we explore all valid neighbors of the current cell. For each neighbor, we ensure it is within the grid bounds, is not flooded, and has not been visited yet. If the neighbor is valid, we mark it as visited by setting its value to -1 and add it to the queue for further exploration. This process continues until the queue is empty or we find a path to the bottom row. If the BFS completes without reaching the bottom row, it means there is no valid path for the given day, and we return false. This result is used by the binary search in the main method to adjust the range of days being tested. Overall, this implementation effectively combines binary search with BFS to determine the latest day when crossing is still possible, ensuring both efficiency and clarity in solving the problem. In this example, we are tasked with finding the last day we can still cross a 3x3 grid before it becomes impassable. First, we initialize the binary search range with left set to 1, right set to 9, which is the total number of days, and answer initialized to 0. We calculate the middle point mid as left plus right, //2, which gives us 5. To evaluate whether crossing is possible on day 5, we construct the grid using the first 5 cells from the input. The resulting grid has blocked cells marked as 1 and open cells as 0. On day 5, the grid looks like this: the top row has 2 blocked cells, the middle row has 1 blocked cell, and the bottom row is fully open. Using BFS, we then check for connectivity from any open cell in the top row to any cell in the bottom row. Starting from 0, 2, the only open cell in the first row, we explore its neighbors. However, no path leads to the bottom row because all potential routes are blocked. Since crossing is not possible on this day, we return false and proceed to adjust the binary search range. Since crossing was not possible on day 5, we reduce the search range by setting right to mid 1, which makes it 4. We recompute the middle point mid as left plus right, //2, resulting in 2. Now we evaluate if crossing is possible on day 2. We build the grid using the first 2 cells from the input. On day 2, the grid is mostly open except for a blocked cell in the top left corner. Using BFS, we start from the open cells 0, 1 and 0, 2 in the first row. From 0, 1, we find a path through 1, 1 and finally reach 2, 1 in the bottom row. This confirms that crossing is possible on day 2, so we return true. With a valid crossing found, we update the binary search range by setting answer to mid, which is 2, and increase left to mid plus 1, making it 3. We then calculate the new middle point mid as 3 and check if crossing is possible on day 3. The grid for day 3 is constructed using the first 3 cells, resulting in a partially blocked grid with a diagonal pattern of blocked cells. To evaluate the grid on day 3, we again use BFS to check for connectivity from the top row to the bottom row. Starting from the open cells 0, 1 and 0, 2 in the first row, we attempt to find a path. However, from 0, 1, the path to 1, 1 is blocked, preventing any connection to the bottom row. As no valid path exists, we conclude that crossing is not possible on day 3 and return false. With this result, we reduce the binary search range further by setting right to mid 1, making it 2. At this point, the binary search concludes, as left exceeds right. The latest day on which crossing is still possible is stored in answer, which is 2. In the second example, we work with a smaller 2 by 2 grid. We begin by initializing the binary search range, setting left to 1, right to 4, and answer to 0. The middle point mid is calculated as 2. To check if crossing is possible on day 2, we construct the grid using the first 2 cells from the input. On day 2, the grid contains 2 blocked cells, 1 in each row. Using BFS, we start from the open cell 0, 1 in the top row. However, the path from 0, 1 to 1, 1 is blocked, making it impossible to reach the bottom row. We return false and adjust the binary search range by setting right to mid 1, which makes it 1. We then compute mid as 1 and evaluate if crossing is possible on day 1. The grid on day 1 is constructed using the first cell from the input, resulting in a fully open grid. On day 1, the grid is completely open, so we proceed to use BFS to check for connectivity. Starting from the open cells 0, 0 and 0, 1 in the top row, we easily find paths to the bottom row. For example, from 0, 0, a path leads to 1, 0, and from 0, 1, a path leads to 1, 1. This confirms that crossing is possible on day 1, so we return true. With this result, we update the search range by setting answer to mid, which is 1, and increase left to mid plus 1, making it 2. As left now exceeds right, the binary search concludes. The latest day on which crossing is still possible is stored in answer, which is 1. Here, we explore the time complexity of the solution, which combines binary search with a BFS traversal. The binary search operates on a range from 1 to the length of the cell's array, splitting this range in half during each iteration. This results in O log n iterations. For each iteration, the canCross function is invoked. Within this function, we first construct the grid, initializing it to zeros. This grid setup takes O row asterisk call time, as the grid dimensions are based on the number of rows and columns. Additionally, for the first day cells, we update their values to 1, which requires O day time. Since day cannot exceed n, this step is capped at O n. Once the grid is ready, we perform a BFS traversal starting from row 0, exploring reachable cells. In the worst-case scenario, BFS would visit all cells in the grid, resulting in O row asterisk call complexity. So, each binary search iteration involves both grid construction and BFS, making these steps the primary contributors to the overall complexity. Now, let's consider the overall time complexity. Binary search performs O log n iterations, and for each iteration, we execute grid construction in O n time and BFS traversal in O row asterisk call time. Combining these, the total time complexity becomes O log n multiplied by the sum of O row asterisk call and O n. This simplifies to O row asterisk call plus n asterisk log n. Shifting to space complexity, the largest contributor is the row x call grid used in the cancross function, which takes O row asterisk call space. The BFS queue also requires O row asterisk call space in the worst case, as it may store all grid cells. Apart from these, a few auxiliary variables like left, right, and answer use O1 space. Therefore, the overall space complexity is determined by the grid and BFS queue, resulting in O row asterisk call. Let's compare this optimized approach with a naive solution. A brute force method would simulate every day from 1 to n, performing BFS for each day. This would result in a time complexity of O n asterisk row asterisk call, which is far less efficient than the binary search approach. The optimized method reduces the number of days to check from O n to O log n, combining this with BFS, which leads to a time complexity of O row asterisk call plus n asterisk log n. This improvement is particularly significant for large grids. Considering the best, average, and worst cases, the best case arises when the binary search quickly finds the solution, reducing the number of iterations. However, the BFS traversal still dominates the complexity. In the average and worst cases, the complexity remains the same, O row asterisk call plus n asterisk log n, as the number of binary search iterations and BFS traversal steps are the primary factors. To mathematically reason through the complexity, binary search reduces the range logarithmically, which accounts for the O log n iterations. For each of these iterations, two key operations dominate the runtime: constructing the grid and performing BFS traversal. Grid construction takes O n time because we initialize the grid and update the first day cells, while BFS explores all reachable cells, taking O row asterisk call in the worst case. When these are combined, each iteration has a combined complexity of O row asterisk call plus n. Multiplying this by the O log n iterations of the binary search gives the overall complexity of O row asterisk call plus n asterisk log n. This formula encapsulates the contributions of grid size, represented by row asterisk call, and the length of the cells array, represented by n, to the total runtime. When tackling this problem, there are a few common mistakes to watch out for. First, failing to update the grid correctly when marking cells as blocked can lead to invalid simulations. It's essential to ensure that the grid state reflects the blocked cells accurately for each day, as any discrepancies will affect the pathfinding checks. Next, choosing an inefficient pathfinding algorithm, like using DFS without proper optimizations, can cause major performance issues on larger grids. Algorithms like BFS or UnionFind are generally better suited for these scenarios because they handle connectivity checks more efficiently. Finally, watch out for edge case oversights. For example, what happens if the grid is fully blocked or entirely open from the start? Missing these edge cases can result in incorrect answers or runtime errors, so it's crucial to test scenarios like a 1x1 grid or where all cells are blocked on day 1. Another common pitfall arises with UnionFind initialization. If you forget to connect the virtual top and bottom nodes or improperly manage the parent array, it can disrupt your connectivity checks and lead to incorrect results. This is a critical detail to get right because UnionFind relies on these virtual nodes to assess whether a path exists across the grid. Additionally, the binary search approach must be optimized. If you don't combine binary search with an efficient pathfinding method, you might end up sequentially checking each day, which significantly increases the time complexity. By integrating binary search with a faster algorithm like BFS or UnionFind, you can reduce unnecessary computations and improve the overall efficiency of your solution. When preparing for interviews, it's helpful to recognize common patterns in problems like this one. This question often falls into categories involving connectivity, pathfinding, or dynamic grid updates. You should be ready to discuss the trade-offs between algorithms such as BFS, DFS, and UnionFind, explaining why you chose one over the others. Optimization is another focus area. Interviewers may expect you to identify a brute force solution and then optimize it. Highlighting techniques like binary search combined with union find or BFS can demonstrate your problem-solving skills. Edge case awareness is also important. Be sure to explicitly mention and test scenarios like grids with no blocked cells, fully blocked grids, or minimal dimensions like a 1x1 grid. Lastly, strong communication is key. Clearly explain why you chose specific algorithms and data structures. For instance, you can discuss how union find optimizations, such as path compression and union by rank, improve efficiency compared to other approaches. Several related problems can help you strengthen your understanding of this type of challenge. For example, LeetCode 200, number of islands, involves checking connectivity in a grid, making it conceptually similar. LeetCode 130, surrounded regions, focuses on marking and tracking regions in a grid, which overlaps with some aspects of this problem. LeetCode 547, number of provinces, uses union find to assess connectivity, but in a graph-based context. Finally, LeetCode 778, swim in rising water, combines binary search with pathfinding, offering a similar mix of techniques. If you're exploring alternative approaches, brute force simulation is one option. This method involves blocking cells day by day and checking for a path after each update. While simple to implement, it's inefficient for larger grids because it has a time complexity of n squared per day. A more efficient option is binary search paired with BFS or DFS. This approach finds the earliest day when a path is blocked by narrowing the search space, but it may still be slower than union find for very large grids. The most optimal approach involves combining binary search with union find. Here, binary search is used to pinpoint the earliest day when crossing the grid becomes impossible, while union find efficiently tracks connectivity. This method achieves an optimal time complexity of log n *n, making it well suited for larger grids. However, implementing it requires careful attention to detail, especially with union find optimizations. Techniques like path compression and union by rank are essential to maintain efficiency and prevent bottlenecks. By mastering this approach, you can solve the problem efficiently while demonstrating a deep understanding of algorithm design and optimization. Thanks for joining us. To recap, we used a combination of binary search and union find to solve the problem efficiently. Keep practicing grid traversal and connectivity-based problems to sharpen your skills. Don't forget to like, share, and subscribe for more content like this. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!